So this session will be chaired by Dr. S.K. Bhattacharya, VC, Shiv, Nadar University. I welcome you, sir, on the dais. Then I would like to invite Shri KRS Narayanan, Business Leader, Carbon Abatement Initiatives, Reliance Industries. Thank you, sir. To represent NCB, I would request Dr. D.K. Panda to join the dignitaries and take this session forward. Thank you, sir.
Good morning, everybody. Today, the first session in this hall is Net Zero Emission Carbon Capture, Utilization and Storage CCUS. And this session will be chaired by Dr. S.K. Bhattacharya. He is Vice Chancellor, Shiv Nadar University. I'll give brief of him that he is former professor, HOD, and Deputy Director and Director officiating at IIT Kharagpur, and currently he is Adjunct Professor of SIR. He was former Director of CSIR CBRI at Roorkee. To his credit, he has more than 250 publications of papers, also published 5 books and book chapters. He has 3 patents to his credit also. He is Fellow of National Academy of Sciences, Indian National Academy of Engineering, Indian Association of Structural Engineering, and Institution of Engineers. He is recipient of Lifetime Achievement and Concrete Technology of Year Award by ICI, KF Antia Memorial Gold Award, Telcom Best Lecture Award from University of Durban. Now the co-chairman is Sri KRS Narayanan. He is the business leader, Carbon Abatement Initiative, Reliance Industries Limited. About him that he is Masters from Leeds University, United Kingdom, Diploma in Concrete Technology, City and Guilds of London Institute, UK. He is recipient of Young Concrete Scientist, Institute of Civil Engineers, India. He is Fellow of Indian Concrete Institute, ACCE, IRC, and IC Impacts. Established Birla Ready Mix as the top brand in Chennai, India by setting up their first RMC plant. He is member of NCOE, IIT Bombay, and advisory committee member of DST. He has got 30 years in sales, marketing, and business development with expertise in carbon abatement, waste plastics, polymeric and carbon fiber, graphene, and refinery catalyst waste. I welcome Chairman Dr. S.K. Bhattacharya and Co-Chairman Sri KRS Narayan, and I request Chairman to proceed on this session. Please, sir.
Very good morning to you all. Welcome to the second day, the first session. I have with me my co-chairs, Dr. KRS Narayanan and Dr. Panda. In this particular session, which is on net zero emissions, carbon capture, utilization, and storage, we have 6 presentations. The first speaker is on the keynote address, which is by Ms. Katarina Malaga. Is she around? Yeah. She will be speaking on climate neutrality for cement and concrete industries in Sweden. And I request Ms. Malaga to present her paper, and kindly restrict your time to 15 minutes.
Okay.
Okay. Thank you.
Hello. I don't know. It's on. This one? Yeah. Okay. Thank you very much. thank you very much for invitation. And ladies and gentlemen, so I will give you some information about how the strategy for climate neutrality is actually implemented in Sweden. This one is the wrong one. The public, yes, this is my colleague's presentation, so it's. This is not the one. This is not the right one. Yes. No. Not yet. It's not yet. No, no.
It's in the presentation. First problem? Any problem? The presentation there?
Yeah, yeah, sure, sure. Don't fix it. Okay.
Yeah, just changing the presentation.
Yes.
So once it is uploaded, you can.
Yes, sure.
Any problem? They're not loaded.
No, it's.
The other one was put.
Yeah, there are two from us, and it's my colleague who is presenting the second one. So
I think by mistake they must have, because they picked up your name.
yes,
and
and
probably
maybe
they
they just put it in. So it's.
just give a minute.
Yeah, yeah. Don't worry. So it's just like 15 minutes. I'm disappearing. Yeah?
No, maybe. No, don't worry about that.
We switch? We switch? Jan will present first? Yes, okay. So my colleague will present and I will come back.
So next before this colleague. Okay. So we'll go to the next one. Yeah, you can go to the first mineral carbonation.
Okay, so we move on to the second presentation, which is on CO2 sequestration potential of various industrial waste and byproducts. It's going to be presented by Ms. Richa Mazumder.
The first one was this mineral carbonation of
Oh,
artificial.
okay. It's okay.
It's okay. It's okay.
12 minutes.
So kindly restrict your time to 10 minutes, please.
Yes, sir.
Okay, thank you.
Respected Chairman, Co-Chairman, NCB representative, honored delegates, a very good morning to you all. I am Richa Mazumder and going to present the topic CO2 sequestration potential of various industrial waste and byproducts. So this first slide shows the levers that will be implemented to reduce CO2 emission. And here we can see the percentage contribution towards net zero is highest for CCUS. And this slide shows the different methods of CO2 sequestration, which includes geological, oceanic, mineralization, biological, and industrial use. So in our work, we have gone through mineral carbonation technique for CO2 sequestration. So mineral carbonation is a chemical process through which CO2 can be converted into inorganic carbonate in the form of calcite, dolomite, magnesite, etc. So in this work, we have identified different types of industrial products having desired chemical composition and mineral composition. Accordingly, different materials have been identified like steel slags and byproduct gypsum. So the question arises why we have opted for steel slag. As we know that India is the world's second largest steel producer, and for per ton of steel production, around 200 kg of steel slag is generated as a solid waste. And it is present as a huge amount and becoming a source of air, water, and land pollution. Similar is the case with phosphogypsum. Phosphogypsum is present in India and estimated to be 64.65 million ton in the form of legacy stock. So that is the why in this project we have opted for steel slag and byproduct gypsum. And this slide shows the chemical characterization of steel slag. Here we can see that CO percentage in different types of material ranges from 30 to 47%, and the CO2 sequestration potential of potential CO3 production of LD slag is highest because it has highest CO percentage. And similarly, the potential CO2 sequestration is also highest in LD slag because its CO percent is also high. And in comparison to phosphogypsum, which is having 30.66% of CaO, the potential calcium carbonate production is low in comparison to other materials, and since its calcium carbonate production is low, the CO2 sequestration potential is also low. Now in the next table we can see the mineralogy of different types of material. Here we can observe that in LD slag the major phase is present in the form of C2S, whereas in AOD and electric arc furnace slag the major phase is present as mervinite. And in FGD and phosphogypsum, the major phase is present as gypsum. Now, in the later slide, we can see how this mineral composition plays a very important role towards mineral carbonation reaction. So this is the experimental design through which we have done carbonation. We had adopted direct carbonation method, and we have gone through both dry carbonation and wet carbonation method. In dry carbonation method, materials were taken in solid powdered form and kept inside the carbonation chamber, whereas in wet carbonation method, in one case we have added water to make it a slurry, and in another case we have added additives in the form of 1% NOH or ammonia solution. And the environmental condition inside the carbonation chamber is maintained at atmospheric pressure 14 plus minus 0.5% CO2 concentration, 27 degrees Celsius temperature, and 65% relative humidity. I want to say that we have not observed any reaction in FGD and phosphogypsum in the presence of 1% NOH and in addition of water. That is why in case of phosphogypsum and FGD gypsum, we have added 25% ammonia solution, which shows the positive result towards mineral carbonation reaction. And in this first table, we can see the LOI comparison in different type of steel slag. Here, the increase in LOI in different types of steel slag shows the increase in mineral carbonation reaction, which shows the formation of calcium carbonate. In the first, and which is further confirmed by XRD graph also. In the first graph, we can see that in the LD slag, which is shown here in black color, there is no peak of calcium carbonate, that is calcite, but when we have added 1% NO solution or we have added water, a sharp peak of calcite is observed. Similar was in the case of AOD slag, where in the original sample there was no calcite peak, but when we have put the sample inside the carbonation chamber in the presence of water and additives, it shows positive reaction towards mineral carbonation and shows the formation of mineral calcite. And the third graph shows the formation of calcite peak in the EF slag, and the carbonation rate in all the three slags vary. In neutral condition, in AOD slag shows the highest reaction rate, whereas in alkali medium, LD slag shows the highest reaction rate towards mineral carbonation reaction. Now, the reason behind this that in LD slag, belite was present as a major mineral, which shows accelerated reaction towards mineral carbonation, which may be due to the acceleration dissolution of Whereas in the case of AOD and EF slag, belite was present as a major phase and which has shown same rate of carbonation reaction in both types of slag. And this is the TG-TTA graph of phosphogypsum and FGD gypsum. In the original sample, we can see there is no formation of calcium carbonate peak. However, in the case of carbonated sample, a sharp peak of calcium carbonate is obtained at around 800 degrees Celsius. And this slide shows the reaction mechanism in byproduct gypsum towards mineral carbonation reaction. And here, in the presence of ammonium hydroxide solution, calcium carbonate and ammonium sulfate formation takes place. So this graph shows the theoretical and obtained CO2 sequestration and calcium carbonate production in steel slag sample. As I have already told, the potential calcium carbonate in LD slag was the highest, and in LD slag we have obtained about 330 CO3 kg per ton, and in case of EF slag the potential was 613 kg per ton, and in case of alkali medium we have obtained 216 calcium carbonate kg per ton. And the second graph shows the CO2 sequestration potential level. In LD slag, it was the highest, 376 kg per ton, and we have obtained about 145 kg per ton of CO2. And in case of EF slag, the potential was 270, and in case of alkali, we have obtained 95 kg per ton. So here we can see that from this graph that LD slag in the alkali condition shows a quite good potential towards mineral carbonation reaction, and I want to say that we have only added 1% NOS solution, so it may be possible that if we have increased the concentration, it shows a quite good potential towards mineral carbonation. And the next slide shows the theoretical and obtained CO2 sequestration in FGD and phosphogypsum, and the potential in FGD gypsum was 558 kg per ton, and we have obtained almost about 400 CO3 kg per ton, and the CO2 sequestration potential was 258, and obtained in case of FGD gypsum was 176. So that was the conclusion, that mineral carbonation through dry route does not show any carbonation reaction, and however we have obtained positive result in case of wet route, in case of both LD and FGD gypsum, and we have found that the mineral composition or the phases which are present plays a very important role towards mineral carbonation reaction. And we can say that steel slag, FGD gypsum and phosphogypsum show potential for mineral carbonation in reduction of CO2 footprint. Thank you.
Thank you. Thank you very much. 1 second, please. Now it's open for questions. Is there any question from anyone?
I have a question. A short question.
Yes,
You said atmospheric pressure and 27 degrees Celsius. Would you think the carbonation rate could differ if you extend it?
Yes, sir.
Have you tried it out in the
No,
experiment?
sir. We have not tried it. We have, in NCB, we have facility of carbonation chamber, and that operate at atmospheric pressure, so that is why we have tried for that condition only. But we have not done any experiment in increased or decreased level of pressure.
No, do you wish to do that?
Yes, sir.
Okay, because you can plot the amount of CO2 that can be
Yes, sir.
sequestered
Definitely,
permanently.
sir. If we increase or decrease pressure, the potential will be increased.
Yeah.
It has shown in the research.
Okay, thanks.
Any other question? Yes, please. Hey.
Yeah, thank you for a very good presentation. Have you considered or are you planning to include red mud in your, because, you know, there's quite a bit of interest in carbonating red mud which comes from when you extract aluminum.
Yes, sir. We have tried red mud also, but the main problem was that the chemical composition of red mud doesn't show any CaO. That is the main hindrance. In steel slag and FGD gypsum, CaO is already present. Minimum 30% is present, but in red mud, the percentage is quite low. That is the major problem, because if we want to sequester CO2, the material should contain calcium.
I may also add something that this is a real challenge. So far, we are concentrating only on those materials, and probably we are optimistic also that materials which are containing lime. But there are huge quantities of other material in India which are non-lime based. So it's a challenge, and definitely maybe modified, updated, new modified route has to be investigated and followed, so that we can take care of non-lime bearing materials also.
Yes.
I've seen work in China with red mud. They sinter it and then wet carbonate it.
Yes, sir. I have also seen a paper where they have added, in red mud, they have added lime, and then they have tried to carbonate that material to sequestrate. In that way, red mud can be used, sir.
So what we are planning also, next step, that we will take this red mud and use our mine rejects, low-grade limestone materials, which are non-usable in cement manufacture. So they will act as a source of lime, and we will sinter it, what route you just told.
Okay, good.
Thank you, sir.
Okay. Thank you very much. Thank you. Well, I understand that the presentation of Ms. Malaga is now ready. So I think we'll move on to that. The keynote talk by Ms. Malaga, which is on, again, climate neutrality for cement and concrete industries in Sweden.
Thank you very much. I will explain you the way we took in Sweden for climate neutrality for cement and concrete industries. My name is Katarina Malaga. I'm coming from RISE, and I'm presenting this in cooperation with my colleague who will also present later on another presentation. Which one is like this? Just few words about our institute, because I don't think that so many people are actually knowing where we are coming from. So it's RISE is the largest environment for research in Sweden. We are around 3,000 people. The turnover is more or less 350 million euros, which could be also dollar. And our income is coming more or less 50% from the business sector, from 30% from public funds, a part 20% from state funds, and we have also a smaller part which is coming from European Union. We are also the largest environment for test beds and demonstration environment. We have more than 130 of those test beds. 40% of our employees are women, and 30% of our employees are having PhD. So this is just a short explanation of the institute. We work not only with concrete or cement and concrete, we actually do research and development within the most of the areas, everything from pure chemistry, electronics, fire department. We have also digital security. So we have a close cooperation to different disciplines in RISE. So how it started, this journey actually for Sweden to become a climate neutral or fossil-free country. In 2015, the government actually established an initiative, Fossil-Free Sweden. And it was with a goal to create the Sweden fossil-free 2045. this was starting the movement where most of the industries had to prepare a kind of roadmap. Of course, Sweden was very ambitious, and they said that we need to be the first nation in the world that will be fossil-free. So most of those industries prepared their roadmaps, and those roadmaps are actually describing what needs to be done in those different areas to become fossil-free. Those roadmaps are like booklets, they can be downloaded, and they are describing what needs to be done on the short term and the longer term. They've been already actually revised. What we have in Sweden is concerning the cement and the concrete industry is that we are using 2 or 3 cements, but we have only one cement producer, which is Heidelberg Materials, located on the island of Gotland, and then we have one production in the mainland. The amount, like you can see, it's small, but it's more or less enough for Swedish conditions. These roadmaps, when they were prepared for cement industry, then they pointed out, together with the cement industry, with concrete industry actually, what paths we need to take. And one part is, of course, energy efficiency, more biofuels, new cement types. Carbonation is quite a big part of this solution. And the rest, maybe it's even smaller right now, is CCS and CCU. So those roadmaps for cement and concrete came out 2018 with a goal to be climate neutral 2030 already, but on the national level, of course, 2045. Those roadmaps are very good, but if you are not implementing them in the action, then they will stay there on the shelf, and then nothing will happen. Of course, industry at this time was interested in putting all the forces together and try to implement partially parts of those roadmaps. So we created a project, coordination project, national one, BETCRET, which was focusing on climate neutral cement and concrete industry, but with the special focus on implementing. So what we did, we put together some partners to discuss in the beginning how we will go on with this. BETCRET is an innovation-driven project and is supported partly by the Innovation Agency. 2019, we started with 8 partners, and it's easier to discuss with fewer partners in the beginning how we will go on. And of course, we had a lower budget for this. Then we continue it with more advanced implementation. So we had, in the beginning, 19, but it came more organization into the consortium. And then we are still running the BETCRET 3, and we have 26 organizations right now. So you can see that the interest, it sounds maybe not so many organizations, but I can tell you this is representing more than 60–70% of the turnover of the actually concrete use in Sweden. So it's quite large. And as you can see, we have a whole range of different organizations. It's not only the industry, it's also associations, road administration, academia, and also some other actually organizations which are not common when we are talking about the cement industry, like mining, iron mining in Sweden, and of course consultants. So goals of BETCRET in the beginning, what we were actually coming to agreement was that we need to create the information and communication because people need to understand what we are doing. So we created like also a social license to operate, because if we are not making people aware, then they will not really follow why we need to be climate neutral. We looked at the policies, regulation, and standardization, because it needs to be actually accompanied. And of course, the question of economy. So we tried to find the solutions that all this change, transformation of industry needs to be, it always costs money, but it needs to be in the way profitable for the industry. We did not have any statistic in Sweden, how much material we are using. Of course, we know how much cement we are producing, but this is the only one part of the whole picture. So we also aimed at producing the KPIs, key performance indicators for material flows. How much of the climate neutral or optimized concrete we are using. Because cement, we know how much we produce, but it's how it's used. This is also important. We also looked at the innovation procurement, because a public procurement is always leaning towards the lowest price, but innovation needs to be included. Of course, we tried to put on the agenda development of alternative binders. We look at circular economy, recycling, optimization of concrete recipes, and CCU for specifically for carbonation. I will give you just some results from this project. During those last 5 years, we produced quite a lot of information. This is showing in what direction we went. So clays, of course, everybody is looking at clays, but this is in most cases kaolin. But we in Sweden, we don't have so much kaolin, so we use E-light. And we develop a methodology for activating the E-light. So this can be also found in those reports. We looked also at biomass ashes as supplementary cementitious materials, and all the information can be found there. Just going further on, so as I said, we have some established producers of binders. And this is Heidelberg Materials, which is producing cement in Sweden. And then we have also Schwenk, which is not producing in Sweden, but in a Baltic area. And they started to produce the binder with volcanic and sedimentary pozzolans. What we did, we evaluated those materials in full-scale tests in the mine. LKAB is the largest producer of iron, actually in Europe. So we could evaluate this concrete with those volcanic ashes, and everything was actually working well. What we did also, we introduced the new standards, because it was not really allowed in Sweden to use this type of material. So we introduced it this year, the new standard for use of natural pozzolana. We have some production of steel slag or of GGBs, and it was not really used before, but since some years, Svesem is actually increasing the production, but it's still a small amount. It's up to 200,000 tons per year. I see that I have a mixture of Swedish and English, but I hope it's understandable. So we have also a totally different type of company that was developing a new binder. And this is Boliden. I don't know if you are aware. This is a company which is mining copper in Sweden. Very big company. And what we did, we were using the mine tailings, the slag, silica sand, and pyrite, and activating this material, mechanically activated, and we achieved very good binders. Boliden filed 5 patents, and this part of the project was actually listed as one of 100's most innovative projects on the Royal Academy list this year. So it's possible also to develop new materials from different types of waste. I was mentioning those KPIs, and KPIs is always difficult to get what we are looking for, but what we did was we were focusing on GWP, then share of alternative binders, which are used in concrete, and binder content, average strength of the different classes. I cannot show you so much of the information because this will be published next year in January. But anyway, to agree only on those KPIs, it took us 4 years. So it's, even it sounds very easy to achieve some information, but I can tell you it's a really hassle to get through the real data. We created also a type of EPD database for clients that they can look at the EPD, which is Environmental Performance Declaration, showing the impact on climate actually of different mixers. So in the same classes, strength classes, which is also showing that the market is really variating. I'm almost done. We also work with carbonation, design for carbonation, for concrete and concrete waste and ashes. We developed some reports which can be downloaded also. And we also cooperated with Swedish Concrete Association, which was introducing 4 levels for greening the concrete. So thank you very much. If you want to know some more information, I'm more than happy to explain how we work with this. And I can also give you some information where to find our reports. Thank you very much.
Thank you very much, Ms. Malaga, for your nice presentation. Any questions, please? Yeah, please go ahead.
Can you elaborate on the carbon policy of Sweden? Are you working, is RISE working on carbon policies, incentives and penalties if you don't stick to the carbon emissions of cement?
We are following actually the carbon emissions policy, European one. So we are in the European Union. And the thing is that all the transformation of the cement industry needs to be done before all the free allowances for CO2 will be gone in more or less 2032. So we don't have so much time, more or less 7 years, but they are also limiting the number of them during this time. So it's not that 2032 they will disappear. So what we need to do is either, of course, install to take all the measures we can to lower the CO2 in the cement industry. And of course, the final solution is the CCS, which will be installed at 2030 at the largest production plant in Sweden. So this is what we do. Otherwise, it will be very costly because right now the cost, it's also varying, but between 80 and 100 euros per ton. So, yes.
Okay. Any other question, please, from the floor? Well, if you don't have any questions, thank you very much. Thanks for your nice presentation. Our next presentation is on mineral carbonation of artificial lightweight aggregates developed from municipal solid waste, incinerated ashes through autoclaving process. will be presented by Ms. Humaira Athar from Central Building Research Institute. Humaira, please stick to your time on 10 minutes.
Okay, sir.
Okay.
Respected chairperson and present on the dais and all the delegates of the dais. Good morning, everyone. My name is Humaira Athar and I'm from Central Building Research Institute. I think there is some slight mistake. Here it is written NCCBM, but I'm from CBRI. So today I will be presenting my work on lightweight aggregates which are prepared through autoclaving process, and they are made from municipal solid incinerated ashes. These will be the content of my presentation. So I will start with a brief introduction. We are seeing these numbers since yesterday, so these numbers are not new for us. We know that as the greenhouse gas is, the concentration of greenhouse gas is evolving in the atmosphere, which is causing the global warming, and India has set a limit of net zero by 2070. So there are many methods, there are a lot of ways to reduce the greenhouse gas emission. So particularly here I will be talking about the sequestration of carbon dioxide into the building materials. Also, the generation of municipal solid waste is a major issue in our country and all over the world, and due to the rapid urbanization. So here I will be talking about the Indian context. Currently India generates around 62 million tons of the municipal solid waste, which is projected to be increased up to 450 million tons by 2050. And so this waste is dumped into the landfills. Some of the waste is treated like the process like biomethanation, composting. Some of the waste is used in these type of process, and some waste, around 10 to 15%, is sent for generation of electricity in the waste to energy plants. So there we get incinerated ashes. So that process is done to reduce the volume. So we get a reduced volume of around 80 to 90% of the municipal solid wastes. And in that wastes, around 80 to 90% is the bottom ash and rest is the fly ash. But the problem is that this waste is again dumped into the landfill. So there is very less usage of this waste. So in this study, I'm trying to utilize this waste as much as possible and also try to sequester carbon dioxide in the form of artificial aggregates. So previous researchers, they have already used. So some people have used it as in replacement of fine aggregates, but here I will be showing the work on which is done on the light artificial coarse aggregates. So this slide shows that the market demand of lightweight aggregate is increasing yearly, and there are two types of aggregates. One is the natural aggregate, other is the artificial aggregates. So in lightweight category also we have two types of aggregate, natural aggregates and artificial. The natural aggregates, we have some examples like pumice, diatomite, volcanic cinders, etc. While the artificial aggregates, which are generally prepared using the waste materials like coke breeze, foamed clay, bloated clay, etc. So these aggregates, they are used in making lightweight concrete and for thermal acoustic applications, for making precast members, lightweight precast members. So they have lot of use, and also to reduce the dead weight of the structure. The lightweight aggregates are produced using a process like sintering, where the aggregates are burned at high temperature, and they are sintered. Second one is the autoclaving, which is the steam curing, and third one is the cold bonding. And internationally, there are some companies which produces lightweight aggregates like the Blue Planet, Carbonate, Calra Corporation. So these companies, they produce CO2 sequestered lightweight aggregates. In India also we have some companies like Lightag, Sintag, Rivasha. But in India we do not produce autoclave aggregates. So here the objective of my study is to develop lightweight CO2 sequestered lightweight aggregates through municipal solid incinerated ashes. So in this research work, we used around 50% of the bottom ash, 25% of the fly ash with 25% of cement. Earlier we tried to use some replacement material of cement because again cement has lot of carbon footprint, but we did not got very promising results, so we had to continue our research work with this cement only. So the materials were thoroughly characterized using all the advanced techniques, and here the problem with the ashes is that it contains lot of sulfates and chlorides. So we have to remove it because again it is going to create negative impact on the strength of the material. So for that thing we have done a pre-treatment where we have taken a ratio of 1:10, 1 is the material and 10 is the water, and we have filtered, just washed it, and then we have used the washed material in this work. So this slide shows the experimental design. First of all, the material was collected. We just got the ashes from the NCR region, one of the plant, waste to energy plant from National Delhi. Then we have washed it. Then using the pelletization technology, we have developed the spherical aggregates, and after some air drying, we have gone for autoclaving because steam gives better strength to these aggregates. And then finally, after autoclaving, we have kept these aggregates in a carbonation chamber for CO2 uptake. So these are the parameters which were varied, like it is shown here. The pelletization time, the desired shape of the aggregates were achieved after 20 minutes of pelletization, and when the speed was kept around 35 to 40 RPM. And here we have air dried it for 18 to 24 hours, and we have varied the pressure of autoclaving, that is 3, 5, 7 and 10 bars. So these are the observations which were recorded. For lightweight aggregates, the important properties is the bulk density and the water absorption, and we use the code of IS 9142. So as our code says that the bulk density of lightweight aggregate should be less than 950 kg per meter cube. So when we varied the pressure, we found that the bulk density was crossing the limit when we increase the pressure, because when we increase the pressure, we get additional CSH products which increase the weight of the aggregates. So up to 5 bars, the limits were okay. Then water absorption, what we saw that initially the water absorption was more, but after carbonation, obviously there will be more hydration products, more calcium carbonate will be formed, which will fill the pores. So after carbonation, all the results showed that the water absorption decreased, and the limit for water absorption is 18%. The water absorption should be less than 18%. Then we have gone for single pellet strength. The literature proposed this test for the single pellet strength of the aggregates. So here what we take a granule of aggregate and test it under the CTM. So what we see that with the increase of the pressure, the strength of the strength increases, and after carbonation also there is a significant increase in the strength. So we got up to 10 MPa. Generally literature reports 2 to 4 MPa of the strength, but here obviously one reason is the cement, because cement is also providing the strength. So before carbonation, the single pellet strength increased, bulk density also increased, and water absorption reduced. Then we have gone for aggregate impact value also, and it is also within the limit. The limit says it should not be more than 40%, and similarly for the crushing strength also. Then we have characterized these aggregates using the chemical characterization, mineralogical as well as morphological. Using the phenolphthalein indicator test, it was observed that before carbonation, the color of the aggregates were pink, but after carbonation, the color changed to colorless, which shows that these aggregates, they have been carbonated. And then similarly, using the XRD technique, we found that calcite and genite type of phases were observed, and this microstructural studies shows that a compact structure is observed because of the formation of additional CSH gel and additional calcium carbonate products. These are the lightweight aggregates which have been developed. The size ranges from 4 to 15 mm. Similar type of size is available in the market also. And using the thermogravimetric analysis, the uptake of around 5% is obtained in these aggregates. So this is my work. Here I have tried to utilize more and more of the ashes, and in future we can replace this cementitious material with other waste material which has the potential of CO2 uptake. Thank you.
Thank you very much. Any questions, please?
Hi sir, my name is Dr. Balakrishna. Here my question is, I would like to furnish 2 points at here. First of all, what are the toxic metals what we are using right now from the coal, whatever it may be. After getting 800 degree and above the process, the toxicity of the metal will be highly neutralized and will not affect any type of natural activity. First point. Second one is, do you have did any comparative study of the cost effectivity?
Cost.
Yeah.
The toxic materials which are present is...
It's not toxic material. This is about the, whatever the aggregates you have completed na, from the...
You are talking about the toxic heavy metals present in the ashes?
That was a general comment what I would like to give you, first of all. So that will not affect any nature, first, because you have mentioned that affects the nature. The toxic metals, after processing 800 and more temperature, it will not affect to nature because it is highly neutralized. That was closed. Second one is that, do you have any comparison study for the cost effectivity?
Sir, no. Right now we are in the development stage only. Still we have to do the leaching studies. So cost-wise, we have not yet seen it.
Okay.
Any other
Sir,
question?
one thing I would like to add, the cost will be of autoclaving because electricity is going there. Rest, everything is like ash is 75% ash is waste. CO2 we are doing in a pressure pot which do not uses electricity. The cost will be of like 3 hours of autoclaving. Yes. Yes.
Thank you. Well, you have very clearly explained that why you have tried to use cement because of gaining some kind of the better properties. My question is, what kind of cement you have tried to use? OPC, composite cement, or Portland slag cement?
Used OPC 43.
Yeah, it's very expensive. You should try to use at least composite cement or PPC. So maybe you may get better results. And as the question was asked, I wanted to ask what may be the economic viability of this activity. You have already explained that we have not compared. Try to use other than OPC, cement which is less expensive. Maybe this would be better.
Thank you for your advice, sir.
Thank you.
Thank you.
Yeah, you mentioned correctly that the incineration of municipal waste could be toxic. And I read a front page article recently in New York Times that this incineration plant around Delhi is causing substantial amount of pollution. Yes. Anybody has any comment on that?
You are right, Professor. What had happened is in Delhi also there is an evaluation which is taking place at the moment, the Ministry of Environment and Climate Change, on the pollution levels that could happen because of this.
Yeah,
and also the leaching analysis, because that is more crucial when you want to make it usable in concrete or any other material which goes into the road or maybe road applications basically.
So apparently the incineration plant were not taking the kind of, you have to scrub the ash before releasing, and they were not doing it.
You are right, Professor. That is the major concern here. We have one of the largest landfills here, not very far away from this place. So again, there is a lot of efforts being taken by the ministry to ensure that the separation takes place, the characterization of the material. So that's quite important for us to analyze before taking up such projects on a large economic scale.
Sir, when I had talked with that plant, so they told that they have put the SOx and NOx absorbers, and when they release the flue gases in the atmosphere, so they are within the limits. They told this thing, and also they provide electricity to Delhi. So they told that they are advantageous. The incineration is good.
We have not still got the report.
You
Published yet.
need to look into that. Yeah.
Let's see.
You need to look into that, and then, as it is being suggested, maybe you may have to explore with different kinds of cement so that, and
Yes,
then economics part, of course, that comes automatically.
Thank you.
Thank you.
Okay, thank you very much. Well, our next presentation is on mineral materials as carbon sinks and secondary materials for construction. Flipping environmental catastrophe to massive opportunities will be presented by Suchorzewski from Sweden.
Thank you, Mr. Chairman. Jan Suchorzewski, I'm the head of research group working with cement, concrete and concrete structures at RISE, Research Institutes of Sweden. And I would like to present today an overview of the projects that we have in the area. The background for this is that the Swedish cement and concrete industry made CCS a cornerstone in their strategy for climate neutrality. Heidelberg Materials plans to open their CCS facility already in 2030. This one as well? Okay, yes. Capturing 1.8 million tons of CO2 annually. That will reduce Sweden's CO2 footprint by 3%, this one plant. However, CCS comes at a cost that we all know, and it will increase probably the cement price around 3 times. At RISE, we have quite a large portfolio of projects related to circularity, reuse, recycling, but also carbon sinks. Today, I will focus on 3 of them and some results from those. And I will go through enhanced weathering for concrete waste, so low-tech technology and low-cost technology, accelerated carbonation of recycled concrete aggregates, also direct and indirect carbonation of incineration ashes, so follow up on the previous presentation a bit, and also our work to use supercritical CO2 for materials that are much more difficult to carbonate in normal conditions. The first project we worked with together with the biggest entrepreneur in Sweden and one of the biggest concrete producers, and we've established a field test for evaluating natural carbonation of concrete aggregate in different fractions, in different storage methods, and we tried to establish a methodology to evaluate the CO2 sequestration potential in that material. So we studied 3 different storage methods, weather protected, non-weather protected, and also traditionally in the piles. We studied 3 fractions and 3 different depths of exposure. And the evaluation or the testing of the material was performed in 3 steps by sorting, drying and homogenization, then stopping the hydration using isopropanol, milling down the material, and TGA analysis of around 50 milligrams of the material. This is also, of course, a challenge, how to find the representative sample from a coarse aggregate. And it's concrete, it's not just cement. We had a good background. We used the material from one demolition project in Stockholm, so we could evaluate the drill core actually before the exposure, and we've evaluated the material after 6 months, 12 months, and we are coming to 24 months in January, so we'll have full results. A few conclusions. What we saw that it's only first 10 centimeters actually of the layer that is carbonating effectively in this type of exposure after 6 months. We of course see variation between the different fractions, and the bigger the fraction, of course, the bigger the spread of the carbonation potential, and the highest carbonation potential in fine fraction, of course, because it contains a bit more cement than the large fractions. And concerning those results, we see that we can sequestrate around 100,000 tons of CO2 annually if we would carbonate all concrete wastes in Sweden every year. So not big number, but very easy, low-hanging fruit. The other project we worked on was concrete produced actually in the lab. We've prepared 7 different mixes containing of Portland cement reference, but also mixes with GGBS, fly ash, limestone filler, and calcined clay, and the tertiary binders of those, tertiary combinations. We worked with 3 different fractions, so the material was crushed after 1 year and exposed to 4 or 16 hours of 10% CO2 in different conditions, temperature and humidity, trying to simulate the industrial flue gas, actually, from incineration plants. And we've tested the aggregate properties before and after carbonation, water absorption, density, and also used it in new concrete and compared the basic concrete properties for those materials. What we saw is that already after 4 hours, we have actually fully carbonated material for smaller fractions. So 16 hours is not relevant. We could even probably go down. And of course, we see that the carbonation potential varies depending on the binder used in the original concrete. Now this presentation stopped. Right. Okay, then we went to the incineration plant and did actually the test in the real facility with actual flue gas. And we found that these results from the lab were quite comparable. Of course, depending on the fraction, we have higher potential for finer fractions and lower in the coarser fraction, and a little bit of variation depending on the temperature and humidity used. But we can capture between 2 and 4% of mass. Another project that we worked on is using actually carbonating the incineration ash. We have a partner company, Ranxels, that have their process for cleaning the ash from all the types of salts and mainly from chlorides, and making it useful for other industries. Ranxels is producing around 110,000 tons per year, and theoretically, based on the chemical composition, high calcium and content, we could sequestrate around 24,000 tons per year. It's also not a big number, but for Ranxels, it's around 50% CO2 of their operations, so it's quite significant. We studied 3 different processes: dry carbonation, which of course has the lowest potential, around 10% of theoretical maximum uptake. We studied aqueous carbonation, which had much higher potential, around 60% of the theoretical maximum uptake. And indirect carbonation, also purifying further the material, leaching out the metals, and also at the end precipitating very pure calcium carbonate that could be used as a resource in other industries. So comparing those methodologies, the indirect carbonation is of course the best, but also requires a bit of investment in the process, more than aqueous carbonation. Actually, that is quite easy to implement in the already ongoing process of cleaning the ash. But using indirect carbonation, we could sequestrate around 15,000 tons of CO2 and produce 53,000 tons of calcium carbonate per year. So there is also an interesting business case in this study. So we evaluated the potential of revenue of around 17 million euros per year. And Ranxels is working on the CapEx side, what type of investments they would need to do to achieve that. And last part is actually a lookout to the project that we've started recently, and that is looking into other types of mineral wastes, mostly mine tailings. We have quite a lot of mine tailings in Sweden, considering that we are 10 million people. We have 50 million ton tailings per year. But we also have quite a lot of metallurgical slags that are not utilized today. Part of those tailings are calcium and magnesium rich, but also have other potentially carbonatable elements. and the slags contain also glassy phases, so they can be potentially used as binders in concrete. In this project, we tried to use supercritical CO2. And for that, we have established a chamber with a capacity of 5 liters that can operate with pressure up to 80 bars to use liquefied CO2 from the CCS plant that will be established in 2030, for instance. We can also add sorbents and liquids and do mechanical steering in the chamber and operate in quite a broad range of relative humidity and temperature. In the project, we also look into methodologies to verify the CO2 sequestration and if it's actually permanent in those materials. To conclude, I went through 4 different projects quite fast, but we followed from the very low-tech and low-cost technology of enhanced weathering through accelerated processes using flue gas. It's also quite low-hanging fruit that can accelerate the process from years or months to 4 hours. We looked into different technologies for the ashes, including purification and also delivering a business case. And at the end, looking to the biggest potential of large volumes. So thank you very much for your attention.
Thank you. Thank you very much. Questions, please.
I have a question.
Yeah, please go ahead.
Since you said mineral carbonation. Now, have you done an LCA analysis on this, particularly with respect to durability? Because you said there is an economic feasibility in this. Durability, feasibility analysis, because the temperatures are quite different compared to what India is and Sweden is. So have you done, extrapolated it to higher temperatures, higher humidity conditions, and environments which are more, with more chloride contents and all that, because you're using artificial aggregates.
In which part of the?
See, I had seen one of the slides in yours, in which you said there's an economic feasibility. You're making money in this. No, I'm trying to ask you, what's the durability feasibility of this?
Well, actually, this material wasn't used in concrete. This was just CO2 sequestration in the ash and precipitation of calcium carbonate. So calcium carbonate with purity of 99% can be used in paper industry, which is a much higher value product actually than using it as a binder in concrete or a filler.
Okay.
So we didn't study durability. We did study durability in the second part, where we used accelerated carbonation for recycled concrete aggregates, and there we see actually that the durability is increasing when you use carbonated aggregate. So we reduce water absorption, and we tested frost resistance, shrinkage, and chloride migration. So we see all those properties are improving when you used carbonated aggregates. And the only thing you need to do is a bypass from an incineration plant to move the flue gas through the material. So it was also very low-tech thing to do.
You haven't piloted it yet?
Pardon?
You have not piloted this yet?
Not yet. That would be the next stage to,
Thank you.
Any other questions, please?
One question from my side here.
Yes, please.
Actually, you have mentioned 2 points. One is the homogenization of the fractions. Which is the best suitable, actually this is connected to that previous question, which is the best suitable homogenization fraction which sustain for a long time, which is in the life cycle assessment. Similarly, you are also doing the carbon sequestration by using low temperature and high pressure method. So what is the best low temperature and high pressure ratio method which is giving the long time of life cycle assessment? See, the basic thing is that in cement, actually LCA, life cycle assessment, is one of the key parameter. Whatever the research we are doing, that should touch that area actually. So this is what is my question related to that actually? What is the best suitable fraction in homogenization to give the best LCA? We suppose the best LCA. And second one is that whatever the best carbon sequestration method which you are using for the low temperature and high pressure, there is up to 80 bar pressure. So what is the good fraction of that comparativity?
Well, I have to say, I hear very bad.
Two questions here,
I hear
actually.
very bad, but I will try to answer the questions. About homogenization, the problem was using, of course, the finer the aggregate, the easier to homogenize it and to get the same result.
That is in compared to the, financial viability also. See, whatever the best financial viability, cost effectivity also should be connected at here. Cost of, see, the more refined will get also always, it is the cost, it's getting more costlier. So
I suggest this question maybe we can discuss, because I really
it's a very pertinent question which he asked. He's talking about the comparison of the cost. I think over a period after this session we'll have a tea session.
Okay.
Hopefully you could catch up with this.
But I can answer the second question about the optimum parameters, and of course we see that the relative humidity around 65%. We tested 50, 65, 80%. 65% seems optimal actually for carbonation. And we used a temperature of 20 degrees, which is the normal temperature. And pressure, we haven't, that was done in atmospheric pressure. Now we are moving to the supercritical CO2, so we will study that and maybe deliver the answer in 1 year.
Okay.
Okay. Any other question? Yes, please. One more question.
Good morning. Very interesting study. For the carbonation of the recycled concrete aggregates, how did you prepare the concrete aggregates? Is it just crushed concrete, or did you separate the sand, or made any attempts to get the fines out?
Yes, the whole goal was not to prepare it in a special way. So in the first study you saw, it was just crushed in a normal industrial way. Also to quite coarse fractions, so we worked also with 0.90, as you maybe noticed. So that's the whole challenge. How do we evaluate concrete, not the binder itself? So sampling of 50 milligrams to a TGA from a few kilos sample, it's a challenge, of course. So we are also working into other possibilities of methodologies to evaluate that, for instance, using the oven and higher mass of samples. And in the second study that you saw with accelerated carbonation, there we had a comfort that we used actually the concrete that we produced ourselves, where the aggregate size was 0.08. So it was quite, much easier to homogenize it and get, comparable results between the fractions.
Very clear. Thank you.
Okay. Thank you. Thank you very much.
I invite Mr. Ashok Kumar Demla and Deepthi Vashni to talk about Indian cement industry. Address held to net zero.
So good morning. So in this paper actually we have tried to give the status, what is the cement industry status, what are the companies who have made announcements that by which years they will make net zero situation, and what are the agencies involved globally for guiding or they are following, and what are the hurdles in India for achieving the net zero and possible pathways. So I'll start with the So if you see the situation at present, I think cement industry contributes around 7% carbon dioxide, and if we don't take action globally, it can go up to 13%. That is what is prediction. So it is very, very important to take steps, because other industries are also taking steps, and rather we have to come to net zero situation by cement industry. Most of the industries are committing in India up to 2050. They want to achieve this target. Next. Yeah. So some of the statements which companies have made, Ultratech, for example, net zero concrete by 2050, they have made the announcements. and intermediate goal of preventing 5 billion tons of carbon dioxide by 2030. Adani has already committed 100 billion of money by 2033 and net zero by 2050. Shri Cement has made the announcement that they will be manufacturing gypsum, which also has some contribution towards carbon reduction. And RE100, they have committed by 2050, they will have all renewable electrical energy. Dalmia already is going very fast and they aim water positive. Yeah, back. Yeah. So Dalmia is setting up a largest carbon capture facility in cement sector and carbon negative. They have announced a little early 2040. So that is the commitment of cement industry, Dalmia. Then JK also committed targets with the reduction of carbon dioxide by 21.7% from 680 base to 532 by 2030. JSW announced that they will be using always slag-based materials, and TSR also they will increase by 30% by 2030. So JK Lakshmi has announced that by 2045 they will have science-based targets initiatives and aim to also increase the water positive from 4 to plus 5% by 2025. So these are some of the announcements. Now, what are the global agencies and how they are connected with the Indian cement industry? There is a Paris Agreement which says that Paris Agreement actually was in 2015. You know, that is the basic initiative that we should have steps so that global warming is 1.5 degrees centigrade instead of 2 degrees centigrade. And they had nationality determined contributors and to cut the emissions and adopt climate impact. There is another agency that is Mission Innovation Cement Challenge that also talks about, that is a part of 24 countries who take initiative on carbon emission reduction. Carbon pricing and emission trading system, ETS, this is very, sometimes very lucrative that if you reduce the carbon, you have some incentive schemes and you can the other industry has to pay who is producing more carbon. So LELAC is another agency which says low emission intensity lime and cement. They in fact capture carbon dioxide emission directly from the production source. So they are pressing on that why not we have double chamber and take the calcium carbonate to CO2 without involving the other gases, like electrical energy can be used. So they are focusing on that, achieve carbon capture by operating the principle of calcium looping. Next. Yeah, World Business Council of Sustainable Development, that is CSI, that aims to propelling sustainability without global cement industry and focuses on effective land and biodiversity management. They also look after the land part of it because a lot of land is used while mining and while making mining activities. So why not rehabilitate those portions also, mining portions, apart from carbon reduction. So then government regulation and national policies that targets on government drives, what government is taking care, and carbon pricing mechanism, how the tax credit should be there. Then the last agencies, which is Global Cement and Concrete Association, GCCA, establishes sustainability charter, increases utilization of alternate fuel and raw materials, improves energy efficiency and circular economy. So these are the agencies globally who are working on carbon reduction initiative. Now, next. Yeah. Coming to the technology, what are the technologies available and how the technologies will take further up to 2050. Carbon capture, utilization and storage, CCUS, which is at present quite costly, but here capture part is post-combustion, pre-combustion, oxy-fuel combustion. So in this direction, I think a lot of steps are being taken, particularly in Europe, and now India is also starting to have a pilot plant for on capture technology, so that we can have some techniques of oxy-fuel production or pre-combustion or post-combustion to see that can we have a plant with all carbon dioxide to be captured. Then utilization part, we can have utilization in some of the chemical production or in enhanced oil recovery or building material, but it cannot be used 100%. So then we are having a lot of research on storage of carbon dioxide, that is the geological storage in certain areas, and long-term safety. When we talk about carbon dioxide geological storages, then we have to see that long-term safety is there and how it is to be taken. So this is the last step which will lead us to the last 50 to 55% of carbon dioxide to be storage somewhere, stored or used in the chemical plants. Now coming to present technology which is already in existence and very much used. One is use of alternate raw materials and fuels, that is fly ash, slag, natural pozzolana and calcined clay. Helps to reduce energy consumption. That is very much active and a lot of steps are being taken. Particularly in India now, I think calcined clay will be another alternative to fly ash. And as we at KHD, we offer flash calciner for producing calcined clay. Of course, there are limitations on quality of clay which can be used. So this is one technology. Then next. Yeah, use or alternate. Then we have another aspect which is alternate fuel or raw materials, biogas or waste derived fuels, decrease the fossil fuel and address. This is one area where Indian cement industry is working very, very hard, and some of the plants have reached up to 35% of alternate fuel also, and some plants are still using 3-4% or 2% of the alternate fuel, but this area will go further. And we at KHD have one system called pyro rotor, where we can have a separate vessel for burning of any type of alternate fuel without much processing in a rotary kiln which is attached to the calciner. So this is very much available and it is working in many countries, and India will have very soon this type of equipment where 85% fuel substitution is possible in the calciner. Now coming to economic policies and feasibilities of our net zero, there are many aspects of it, that is the cost analysis, incentive and regulation, and public and private sector collaboration that is needed. This I will not go through too much. Then there are certain barriers in terms of technical challenges in implementing the CO2. Then infrastructure and investment, I think many people must have talked on this, and societal acceptance. We have to also educate the people for carbon reduction, how we should collect the waste and all these. So a lot of bodies are involved. Next. Now what are the prospective advancement in the future? Scaling carbon capture, utilization and storage, next generation clinker technologies we have to think, electrification part, if it is possible, digitization and 4.0 technologies, circular economy, advanced concrete formulation, nanotechnology, hybrid and integrated cement plants, and life cycle assessment studies. Now coming to the what can be the possible path, foundation phase is already there, 2024 to 30. That is we have to focus on public awareness and policy development in investment in clean technology. I think accelerated pace will come emission reduction strategy and scaling up negative emission technologies. I think by 2050 we have to scale up CCUS and scaling up of renewable energies like solar energy or electrical energy. We have to go a big way, wind energy, alternate energy systems. Next, this is the final. Yeah. So in conclusion, I can see that when we talk about 2050, CCUS will be the technology which will absorb almost 50% of the carbon dioxide, but we have to see the economic part of it. The technical hurdles and the infrastructure limitation and societal acceptance requires a lot of innovations, and policymaker, industry stakeholders and researchers can together try mission towards net zero. So then it will be possible. Of course, companies have declared by 2050 they will do. So all this will relate to involvement of all the agencies to achieve this target. Thank you.
Questions, please.
Sir, I have one question.
Yeah.
For this flash tube calciner which you have developed, what is the fuel type you are using?
In flash calciner, I mean, it can be used the fossil fuel also, and we can use the alternate fuel.
Alternate also can
fuels
use?
also we can use.
Okay. But we have not tried the route of electric heating.
What about?
Electric heating.
Electric heating. Of course, some researches are going on in Australia and in Europe for electrification of clinkerization process, lilac. But the main problem sometimes we see that basically burning is through the radiation heat in the kiln. So whether electrifying the outer chamber and making the calcium carbonate to CO2 or with this, whether that position will come at high temperature, because there are some apprehensions that whether clinkerization will take place, at present clinkerization takes place in the radiation atmosphere. It is radiation heat which goes into the clinker and clinker is made. But if we heat the system from outside at 1600 or 1800 temperature, whether that process will take place to the binding material or not, that is still to be seen.
Okay, then
so some lab scale tests are being done.
Then coming back to fossil fuel and alternate fuels.
Yeah.
Does it require different type of systems or same system will work?
Fossil fuel, alternate fuel.
Alternate fuels.
In alternate fuels, up to some extent, when you use up to 30% or 35%, there is only you have to look after your calciner and the preheater fan and whole system, you can balance it out. But when you start using almost 85% of replacement or 90% of replacement of calciner fuel, you require a separate, burning system. You cannot design your calciner up to that extent that it can be used for 85-90%.
Then in that way, I mean, there is a huge list of alternate fuels. There is a huge list of alternate fuels. So
there is a huge list, and there is need of processing at present. And what we have now designed this pyro rotor, here processing is very less. You can feed up to 200 mm particles in the sort of vessel and burn it, only gases you can take into the system.
So can you list 1 or 2, 3, 4, 5 fuels which you have tried?
We have tried many fuels in this system. Of course, MCF is the easiest one, but wood part in Vienna, there were a lot of wood pieces, 200 mm. So that wood pieces were used. Then we can use complete tire. It is possible without shredding it too much. Just put it tire. You should have the vessel 5 meter diameter and then feeding system also 5 meter, so that you can put the tire. Tires have been used. So municipal waste. Then in Europe they use all this animal waste also. So in fact, one pyro rotor in Austria is able to, serve almost 3 million tons of cement. So this is a big vessel. You can use anything.
Okay, I think
we have some installation in China.
Hello.
That's fine.
Hello.
Yeah.
Yes.
I'm K.K. Roy Chaudhary from Cement Manufacturers Association. Demlaji, your last but 2 slide on prospective advancement, there are estimations available about potential of reduction. So can you please highlight what each of those suggested advancements could
My slides were actually, many people must have talked. It is basically, you have to look after the feasibility, you have to involve the government agencies, and see the techno-economic feasibilities. So all these are known facts. People are talking how municipal waste can be used, what is the government involvement or city involvement to make it presentable, collection in different ways. So a lot of talks I think have been done on this. This is basically the gist of that. But principally when many cement producers are claiming that by 2050 we will achieve the target.
Some ballpark figures against each.
I mean,
some ballpark figures against each.
Against each?
Yes.
Yeah, I think
this
can be taken up separately during
But I will say that up to 40-45% you can achieve the carbon reduction target with the initiatives which are being taken. But 50 to 55% are still to be seen after 2030. When CCUS will become economical viable, then we will see the day that for this, of course, societal acceptability is also there. If I say that carbon dioxide I will put under the earth, so there will be hue and cry in Bay of Bengal or some area. So you have to make societal acceptance, you have to make economic acceptance, and you have to have a government policies.
We need a roadmap. Yeah, last questions here.
I am Dr. A.K. Dikshit.
Yeah.
I have a question. You were addressing about the net zero.
Net zero.
Now question is, you have shown different type of proposal from cement industry. They are getting the funding for different years wise.
Yeah.
But my question is, cement industry now producing 8% your CO2. Is it feasible really to give the net zero in near future after 2030 or 2040 or 2050? Because at 2070 we will not be alive, most of the people.
That is what I am focusing, that there are now at present whatever technologies we are talking, we can achieve up to 40 to 45%. How? Alternate materials we use, pozzolana, slag and all. We use alternate fuels, different type of fuels. I think it will get stabilized in the coming 5-10 years. I mean, there will be a lot of efforts. But still you have to do 50-55% of the carbon reduction through carbon capture and its either utilization as additive in the chemical industry or store it under the earth. So that is the big challenge where we have to work a lot.
I think we stop here because you can have more discussion during the tea break. We are running short of time. Yeah, please. Okay. Thank you very much.
Thank you. I now invite the team from CSIR CBRI on the paper on evaluating the feasibility of acceleration carbonation curing for sustainable construction. Akash Padmalal, Kishore Kulkarni, Pradeep Rawat, and Srinivas Rao Nayak. Kulkarni is presenting.
Yes. Yeah. Thank you, sir.
10 minutes.
Yes. Thank you, sir. Dignitaries on the dais, delegates and participants. So, good morning, everyone. The title of my presentation is Evaluating the Feasibility of Acceleration Carbonation Curing for Sustainable Construction. So, in the CSRI, we are working on the CCUS mission mode project. Under this project, there are various packages are there. And out of this one of the packages is this utilization of CO2 in construction industry. So my content of presentation is introduction, objective, experimental work, result discussion and conclusions. As we are aware that global warming is taking place and because of that one there are a lot of many problems are there. And the main is deforestation and the industrialization, these are the reasons are there. And which leads to greenhouse gas emissions. Because of this one, we are facing the impacts of climate changes that we are aware. And if you look at the India and the CO2 emissions, we are at 8.10, that is we are at the 3rd place next to United States. And because of this one, people are talking on the utilization of CO2 in various ways. So one is the challenge is the capture of the CO2, another is the utilization and the storage. So in the CO2 emissions, there are different sectors which are contributing. That is one is the coal, that is the most contributing CO2 emission, and the cement industry is also one of the sector which is also contributing to the CO2. And but also in the other way, the cementitious product can utilize that emitted CO2 in terms of the accelerated carbonation. So there are many initiatives that have been taken place, as I mentioned. So one is the CO2 sequestration. Earlier days we used to work on the carbonation, but we used to consider the durability aspect out of the concrete carbonation. But nowadays as we are finding out, there is a potential of the accelerated carbonation through which we can able to sequester the CO2. So with this we have started the work, and in this we have fixed up the objective, that is what the effectiveness of the accelerated carbonations, wherein we are considering the concrete, base concrete, and we are finding the concrete strength and the other properties we are finding how it is affecting. And we are comparing with the conventional water curing. So as we are aware that this is what the concrete which contains the aggregates and the pores, and we know the internal composition of the concrete, that is what the calcium hydroxide and the CHL gel. So unhydrated part which may react with the CO2 and which again form the calcite, that is the calcite formation will take place, and that is what a dense structure which can that is what calcium hydroxide can convert into calcite. So we have started the experiment by considering the concrete with having a different compositions. That is what we have added the fly ash with the replacement of 10 to 30%, and then we have taken the samples to the accelerated carbonation, wherein we have considered the temperature, that is optimum conditions we have attained at 35 degrees centigrade temperature, relative humidity of 70, and the CO2 concentrations we have taken 10%. And here in two set of cubes we have cast. One set we have taken for the water curing, another set after the casting, after 24 hours of demolding, we have taken these specimens for the carbonation of 6 hours, 24 hours and the 72 hours. And after that one we have determined the properties, physical and the mechanical properties like compressive strength, pH, and some characterizations we have done by some instrumentation. And these are the results of all the four mixes, wherein M1 is the base mix, which is purely OPC, and the other three mix wherein addition of the fly ash is there. As we can see from this mix, as the carbonation time increases, the carbonation is taking place, and we are getting the we are finding the strength increase in the concretes, and as compared to the water, the carbonated specimens which are having a higher strength, and as the fly ash content is increased, the strength is obviously decreased. But even though there is a carbonation potential in these specimens as well, and we could find that optimum mix we can able to find between the 10 to 20%, that is M2 or M3 mix. So then we have find out the pH, because as we know that carbonation is taking place, then the alkalinity of the concrete which get reduced. But we could find for all mixes, even though alkalinity is pH level is getting decreased, but which is in the range wherein we don't have to worry on the corrosion of the reinforcement. And by using the phenolphthalein indicator, we have determined the depth of the carbonation. As we know that concrete having a dense microstructure, the carbonation depth is very much less, which is we could find 5 mm to 6, 7 mm up to that carbonation depth we could able to find, and the internal part which is not carbonated. And then we could able to find the microstructure of this one, and through this as we can see the figures of A and C, which is for the water cured, and the B and D, which is for the carbonated one. And we could find there is a formation of the calcite in the concrete, and this is again we have verified with the XRD, and we could able to find the peaks of the calcium carbonate formations in the carbonated. These are the peaks which is for the M3 mix, that is 20% fly ash mix with 72 hours of the carbonation. So with this, the conclusions of this basic work, that is what there is a positive effect of the carbonations and we can able to sequester CO2. And we have done the CO2 uptake by finding out the TGA. We could able to get the 6 to 8% of the CO2 uptake through TGA on the specimens what we have taken from the surface. And then the pH level which is within the threshold limit to prevent the corrosion. The carbonation depth is around 5 to 7 mm, and the microstructure, we are getting the denser microstructure. We can see that the pores are getting reduced and calcite formation is taking place. And we are thankful for the sponsoring this project to our headquarters CSRI. So under the HCP 48, this project is funded. So thank you. Thank you.
Thank you. Maybe one or two quick questions.
I have a quick question in this. So working on the projects here. Dr. Kishore, can you just tell me two things? One is you said pH is coming down to 12.2 from 13 and 72 hours. Have you studied beyond that? Number one. Number two is on the grades of concrete. If you have a lesser grade of concrete, can I assume that there will be a more uptake of CO2 because there's more pores available inside the matrix?
Regarding your first point, sir, we have not studied after 72 hours of the pH. And with respect to, as you are right, that if the lower grade of concrete is there, obviously pores are there and CO2 ingress will be more in that. So obviously carbonations will be more.
But you have not studied that?
We have done with the normal strength concrete only. We have not done with the high strength concrete.
Normal strength means what is the grade?
That M25 grade we have studied, sir.
Okay, thank you very much. The last question.
Hello. My question is that you have tried with 100% pure CO2, right? So have you tried with any composition that contains around 25% CO2 like this? So what will be the behavior of the product?
Yes. So at present we have done, as you are rightly mentioned, that we have done the pure CO2 up 99% pure CO2. And in future we are having a planning of doing the CO2 sequestration with the flue gas. And for that one particular industry also we have identified, and there we are making the setup so that the real scenario can be simulated through this. So that work is undertaking.
Yeah, the one more difficulty with flue gas will be the temperature. I hope you are catering that also.
Yes, yes.
Okay, thank you.
Okay, thank you very much.
Thank you.
Thanks.
Now I invite the last presentation of the session. Carbon capture, utilization, storage to cement industry, considerations in business case development by David Giant and Havoksin Jiu, Department of Waste to Energy and Carbon Capture, Rambol.
Good morning. I'm the last speaker, so I'll try to be very quick. My name is David. I'm from the Department of Energy from Waste and Carbon Capture at Rambol.
A bit louder, please.
All right. Rambol is a global engineering and consultancy company spread across the world, headquartered in Denmark. We have around 18,000 experts working in different fields, primarily catering to 7 different markets. I don't want to go into the details of it. But pertaining to this particular talk is our involvement with almost 20 ongoing carbon capture projects. In the last many years, we've also been involved in close to 180 CCUS projects. We advise clients from various industrial CO2 sources like cement, starting from the concept development of the carbon capture plant to its integration to the cement plant to detail engineering, as well as doing EPC or EPCM of the entire phase of the project, starting from concept to construction. Now, coming to cement, cement has many different options for decarbonization, and CCUS is one of them. I don't want to go into all the details, but specifically talking about carbon capture, cement has certain specific unique challenges that it poses. Of course, there are many. I'll try to highlight few, starting with the need for conditioning the flue gas before the capture plant. This is more than what we are normally doing to meet the emission regulations, be it NOx, SOx, or controls of dust. This does vary depending on the nature of or the kind of technology that will be used for capture. The second challenge, of course, all the capture technologies require a lot of energy. Some require electrical, some require thermal, some require both. So the site needs to be able to provide this additional energy demand that comes from implementing a capture plant. And finally, of course, the location of the plant itself need not necessarily be conducive to the entire CO2 infrastructure. We might not necessarily have a lot of utilization options in and around the vicinity of the cement plants. Similarly, we also know that all the cement plants are not located close to the harbor from where the CO2 can be shipped to an offshore storage site. On the flip side, we also see there are some advantages, of course, depending on how you say it. Cement is considered as a large CO2 point source with a very high concentration of CO2. This can be seen as positive while developing big carbon capture projects in any specific region. All right, so with that kind of a background, earlier this year we were approached by a major international financial organization who's actually considering to support decarbonization projects, particularly in the hard-to-abate sectors like cement, and more importantly, specifically on developing nations. So we started doing a pre-feasibility assessment of doing carbon capture at a cement plant in Asia. And of course, the study starts with technology assessment. There's plenty of technologies out there, all of them claiming that theirs is the best. So we need to make an assessment based on what's good for the particular plant. So what works for one site need not necessarily work for another plant. So we look at criteria like what is the energy demand, what kind of energy is required, what is the concentration of CO2 in the flue gas, amount of flue gas conditioning that's required. There could also be secondary emissions, waste streams produced from the capture plant, which also needs to be taken into account. And of course, the most important is of course cost and the commercial and technical readiness of the capture technology. It wasn't a surprise for us that the post-combustion amine-based capture came out on top for this particular project, but there are others like hot potassium carbonate or using a cryogenic system, as well as some of these oxyfuel calcium looping technologies are kind of catching up. So I don't want to go into the details of the capture technology itself. The cement plant in consideration had 4 clinker production lines, each having a design capacity of 6,000 tons per day of clinker. Of course, the actual production is slightly more. The carbon capture would be connected to the flue gas from one of these lines. What's very important here was the availability of steam. Since there are 4 cement lines and all of them had waste heat recovery units, not only on the pre-downcomer gases, but also on the cooler vent gases, there was more than enough heat energy that was available to support carbon capture on one cement line. So this was also a consideration for choosing a post-combustion amine-based capture system. And finally, we also did a cost assessment based on our experiences from Europe, looking at CapEx, OpEx. The total cost of capture alone comes to around $60 per ton of cement, per ton of CO2, sorry. But what was worrying is the transport and storage cost. And this was quite obvious because in this region, this being the first mover project, there is lack of CO2 infrastructure for moving the CO2 after it's being captured. So the CO2 from this plant should be captured, after it's been captured, should be shipped via trucks to the nearest harbor, which is maybe 20-30 kilometers away, and then to offshore storage sites, which is about 100 to 200 kilometers away by ships. And this is very expensive compared to just doing just doing liquid transport or gaseous transport through pipelines. We also try to look on what are the revenue streams that are possible. There could be some revenue coming or income coming from utilization options, like some of the papers that discussed about them earlier. There could be some subsidies from the government, but most of the, or majority of the cost for carbon capture needs to be supported by either CO2 tax, or this will be passed to the client as a green premium for low carbon cement. Before I wrap up, a couple of other examples from our involvement from Europe. We are supporting Heidelberg Materials for their carbon capture plants in Sweden throughout the entire value chain, from not only just capturing but also shipping the CO2, logistics at the harbor. Similarly, we are also doing a second project on a cement plant in Europe. This is with PSA with cryogenics, so it's slightly different from amines. So in conclusion, I'll say that carbon neutral cement is possible. We'll see the first ones as early as 2030. 2025 at Heidelberg, and more will follow. But what is needed is two actions. One, on the government side, we need policies and regulations around CO2 tax or emission trading system, but also frameworks around licensing and permitting. This is also very important and often overseen. On the market side, the utilization industry needs to improve, not just for producing synthetic fuels, but also for mineralization needs to improve. But all these cannot sustain. We still need an acceptance for carbon neutral cement or low carbon cement, which should be sold at high premium. But the biggest challenge in executing such projects is the multidisciplinary nature of the project itself. We need experts from the cement industry, we need experts from carbon capture, we need people who can do energy modeling, integration, process modeling, heat and mass balance, and so on. We also need electrical engineers for high voltage supply. We also need experts who know how to ship the CO2 out of point sources like cement. So this is where Ramboll fits in with our experience from being in the oil and gas industry for many years, and with our involvement with carbon capture projects all over the world. I think we could consider ourselves as an honest engineer supporting many of these carbon capture projects. Thank you.
Thank you. Thank you. Maybe one or two questions you have. Any question, please? No? Okay. Thank you. Thank you very much. So we come to the end of this particular session. As we have seen that we had quite a few nice presentations, and I think we all realize that that's the order of the day that we are looking for, net zero emissions, carbon capture. Many aspects are being talked about, but it's important that now we start thinking about quantifying things, have proper roadmaps, how to execute it and get the things done. And I think that's where we need to zero on. And if we move forward, I'm sure that we'll be able to achieve that. Yeah, I request my co-chair to make a comment.
Quick brief. All the presentations are very well made. In fact, carbon capture utilization is, I probably feel, the most important part. The storage can be left apart. CCU is quite crucial now. And out of CCU, I think CU is the most important thing. Most of us have figured out how to capture carbon dioxide. Now, how do you utilize it is the most important thing, because we cannot capture it and keep it somewhere. And storage is very expensive, transport is very expensive. So the lowest hanging fruit to me in the last 4 years, I've been working with most of the industries, is the lowest hanging fruit is cement and concrete and building materials. Very inexpensive to push CO2, permanently sequester it, rather than any other means. Conversion into various other products, petrochemical products and etc. are slightly expensive. But I think we should work on cement and concrete. Alternate fuels is going to be very, very crucial. And in my opinion, hydrogen will be a very important fuel source. in the few years to come, which could propel the cement industry. The burners have to take, the asphalt industry has already started to embrace hydrogen burners in Europe. So hopefully the cement plants will also start gearing up for hydrogen burners, which is going to be a reality now. Electricity will be a little expensive, so hydrogen. Carbon storage, I'm not very sure about how it's going to work in the future, because the storage itself, geological storage itself is very expensive, and we don't know the long-term effects of the geological storage. So overall, it's been a very nice time. Great presentations from all this. Kudos, congratulations to all the people. Thank you.
Thank you. Thank you very much.
Thank you, sir.
We have, yeah.
Now I would request Chairman to present memento and certificate of participation to our keynote speaker, Ms. Katarina Malaga. Thank you, sir. I would also like to request our chairman, co-chairman, and Dr. D.K. Panda to present certificates of participation to all the presenters. For this, I would request all the presenters to come on the stage, please. Ms. Richa, Ms. Humaira Athar, Mr. Jain, Shri Ashok Demla and Ms. Dipti, Mr. Kishore Kulkarni, and Mr. David Jain. Ms. Richa Mazumder. Next, Ms. Humaira Athar. Mr. Zen. Mr. Ashok Kumar Demla and Ms. Dipti Pashning. Mr. Kishore Kulkarni. Mr. David Jayant. Thank you. I would now request Dr. D.K. Panda to present mementos as a token of appreciation to a respected chairman and co-chairman. Thank you, sir. So ladies and gentlemen, that concludes this session. Let us break for a cup of tea, and during tea you can also visit our exhibitor stalls in Hall 1C. The next plenary session 2 will commence at 11:30 in Hall C. So thank you.